Okay, we've so far had quite a lot of exercise with continuous random variables and their probability density functions. Today's topic is conditional probability density functions. So what happens when we condition a random variable x, which is a continuous random variable, on an event, okay? So we'll start by conditioning a random variable on an event. Later on, we'll generalize this to conditioning one random variable upon another random variable, okay? So let's start by this. Conditional Pdf of a continuous random variable x given an event A with probability, positive probability, non-zero probability, is defined by fx given A, the conditional Pdf of the random variable x conditioned on the event A, which is equal to the density fx of x divided by the probability of the event. Okay, probability that the random variable takes values in the set A if x is in A and 0 otherwise. Okay, this is a definition, but it makes a lot of sense if you think about it. Now, consequently, okay, if you take a set B and you're wondering, given that x takes values in A, what is now the probability that x takes values in B? Okay, this can be computed by integrating over B the conditional Pdf fx given A of x. Now, if B is outside of A, what should be the result of this? 0, right? Because if x is in A and B is outside of A, then x cannot be in B, right? So if B is a subset of A, computing this probability will make a lot of sense. It will further refine our information on x. Okay, we know that x is in A. Now, what is the probability that x is in a smaller region within A? B does not necessarily have to be a subset of A, of course, in order for us to compute this, and in order for this to be non-zero. Anyway, I think it will be clearer once we do an example. Let's think about this example, about the exponential random variable. Okay, so I hope you remember the exponential Pdf. If not, let's remind ourselves. Fx of x, fx of script x, is lambda times e to the minus lambda x when x is positive or 0. Okay, and 0 otherwise. This is a one-sided probability density function that looks like this. It's parameterized by just one parameter, which is lambda. Previously, we showed that lambda is related to the rate of decay of this curve. And in fact, the expectation occurs right at 1 over lambda. You remember this? Okay. So now we are given some extra information about this x. We are given that event A happened. Event A is the following. Event A is the event that x is bigger than t. Okay? So the light bulb has already been operating for the first t time units. Now that we know that, we cannot really say it's exponential anymore, can we? Because as you see, the exponential starts at 0. Okay? The exponential density starts at 0 and decays up to infinity. But now that we know x is at least t, suppose t is somewhere here, we we cannot say anymore that x is exponential. The conditional density of x will be different. Let's compute what it should be. Let's apply the definition up here, which is the definition of the conditional Pdf. Okay. So f x given a is equal to fx of x, which is lambda e to the minus lambda x, divided by the probability of a, which is in this case the probability of x being bigger than t. This is the case, of course, when x is in A, which means x is bigger than or equal to, no, in this case it's bigger than t, and it's 0 otherwise. Any problem with this? We know that the conditional Pdf will be restricted to this region. It will be restricted to this region. We just don't know the shape yet. This is for us to determine. So let's continue with this. What is the probability that x is bigger than t? We computed this before. If you remember, this is something that I asked you to learn about the exponential random variable. The probability that the random variable exceeds a certain value t, if that random variable is exponential with parameter lambda, is exactly e to the minus lambda t. Do you remember this? Okay, you can always take the integral, evaluate the integral of the density from t to infinity and convince yourself that this is the case. Okay, so this is the case when x is bigger than t and the conditional density is 0 otherwise. So computing this, we get lambda e to the minus lambda x minus t. Right? Whenever x is bigger than t and 0 otherwise. What does this look like? Let's plot the conditional Pdf here on the side by side with the unconditional Pdf. Fx given a, x given a. Now it's 0 up to t, which we were expecting anyway. At t, it becomes lambda, right? So it's at the value lambda right at t, and it decays like this after t. So it looks just like the original exponential Pdf, only it's shifted to the right. This is a very remarkable property. It's called the memorylessness property of the exponential random variable. Exponential random variable is memoryless. This means that given that it's bigger than t, its Pdf at x plus t is exactly equal to the Pdf of an exponential evaluated at x. In other words, it loses its memory. At every time t, now that the lifetime has surpassed t, the remaining lifetime is still exponential, as if this light bulb has not spent any time in operation. Okay? This is just like the geometric. If you remember, the geometric random variable, which corresponds to the number of trials until success, up to and including the first success, that is also memoryless. Given that I have tried n times so far, does not influence the future distribution of my trials. just like that. And we saw, in fact, when we were talking about the exponential, when we were computing the expectation of the exponential in a few classes ago, the similarity between the geometric random variable and the exponential random variable. Anyway, the topic of this example, the purpose of this example was conditional PDFs, and I hope it is now a little more clear why we define the conditional this way. So essentially what we are doing is similar to what we did in the conditional Pmf case. We restrict the values of the random variable, the values that random variable can take, to the conditional region. You know, x has to be in A because we know that x is in A. So outside of x equals A, or outside of this A, the PDF has to be 0 now. Okay? And then what we're doing by dividing by the probability x equals A, I'm sorry, maybe the probability that x is in A, there's a typo here, is just normalization to ensure that the resulting conditional PDF is a legitimate PDF that integrates to 1. All right. Now that we have defined and understood conditional PDFs, we can extend conditional expectations to the continuous case using these conditional PDFs. So let's consider the expectation of x given A. The expected value of x given A when x is a continuous random variable. How would you define it? Simply integrate x times the conditional density fx given A dx over what region? Right, outside of A, the conditional density is 0. So this is integrated over values of x that are in A. That's pretty straightforward. How about the expectation of a function of x given A? Again, the previous results from the discrete case extend easily, and it will be easy to show that they extend because the summations there are simply replaced by integrals. X given A dx. Let's do an example for these. All right. Here's the example. The voltage across a certain power source is known to be between 4.8 to 5.2 volts, but it's random. Okay? Perhaps it depends on certain environmental conditions, etc. Okay? And it's uniformly distributed between 4.8 and 5.2. The DC current supplied to the system from the source is non-zero only when the source voltage exceeds 5 volts. So the system doesn't work when the voltage is below 5, suppose. Okay? And then once it works, the current is linearly proportional to the voltage. Let's imagine. Okay, let's assume. With a constant of proportionality A. Given that the system is working, compute the expected value of the power generated by the source. Let's understand this problem. We have this voltage V, which is given to be uniformly distributed between 4.8 and 5.2. So it's a continuous, uniform random variable. What else do we know? We know that current is proportional to the voltage when the voltage exceeds 5 volts. Given that there is current, what does that mean? Given that the voltage exceeds 5 volts, right? So the event A is, in this example, the event that V is bigger than 5. Does everyone agree? The event A that we're conditioning on is the event that V is bigger than 5. What is the question? Question is, find the expected value of the power under the condition A. Okay. Now, here we need to have a relation between power and voltage and current. So what do you suggest? Okay, as electrical engineers, I think we can form a relationship for these. Let's say P, excuse me? Well, it says the constant of proportionality is A and the current is linearly proportional. So I would say I is equal to A times V, according to the statement of the problem. So AV squared, how about that? Let's accept this as a given. Provided V is bigger than 5, and it's 0 otherwise. This is P. Is P a random variable? Yes. P is a random variable which is a function of the random variable V, just like g of x here. Computing the expected value of g of x given A is something we considered in this equation. Just like that, we are computing the expected value of P, which is a function of V, given A. Right? So find the expected value of P given A is the question. How do we do this? If you look at this equation, we need the conditional density of the voltage V given A. So let's compute that. It may be worthwhile to just plot the unconditional density first. It's uniform between 4.8 and 5.2. Okay? This is Pf of x, let's say, as a function of x. What is the height here? 1 over 0.4, which is 2.5? Right. The event A, let's mark it here. The event A is the event that the voltage is bigger than 5. Okay? So it's easy to form the conditional density in this case. F V given A, X given A. It's Fv divided by the probability of A. What is the probability of A? Trivially, it's 1/2. Because A corresponds to, the probability of A is exactly this area, which is exactly half of the total area under the Pdf, I'm sorry. So Fv given A is uniform between 5 to 5.2. And its height is 5. Let's write maybe how we got this. It's quite intuitive, but let's write it for the sake of completeness. Fv given A is equal to Fv of x divided by the probability of A whenever x is in A. Okay? But the probability of A is 1/2. So this is equal to Fv divided by 1/2, which is 2 times F sub V. F sub V is 2.5. So we have 5 here. So we now have to compute the expectation. Expectation of P of V. Expectation of the power as a function of the voltage given A, which is the event that the voltage is bigger than 5. So this can be found by integrating A times V squared times F V given A, V given A, dV over the region A, which is 5 to 5.2. So it's trivially, this is a constant 5. We are integrating A times V squared. So we have 5A over 3 V cubed, 5.2 to 5, which is 5A over 3, 5.3 cubed minus 5 cubed. That is the expected value of the power supplied by the source. Any questions? Yes, please. Oh, I'm sorry. Yes, this is 5.2. Thank you. Okay. So, any other? A is just a constant. It could be anything. So, if your idea is a resistance, it could be resistance could be 1 over A. So in this, it says current is linearly proportional to the voltage with a constant of proportional to A. What I understand from this is I equals A times V. So I don't see that there's a lot of ambiguity there, but of course, if that were the case, that would be 1 over A. Not a big deal, really. So.
Hocam,
yes, please.
Voltaj 5'i geçtikten sonra akım lineer artmaya başlamıyor. Öyle dememiş misin?
Right.
Hani ona göre mesela akım şey olmuyor mesela AV eksi 5A gibi bir şey. Akımın V'ye göre fonksiyonu. Hani tam AV square olmayabilir o zaman belki.
But it says when V exceeds 5, the current is linearly proportional to the voltage. It doesn't say it's linearly proportional to voltage minus 5. So, you know, I understand that you're trying to make the problem description maybe fit more into a physical circuit, but, you know, this is the probability example, so don't worry about the circuit behind it, okay? So even in that case, the math, the computation here would not change very much. What we would have is a constant subtracted from this. So let me repeat. Given that this is the relationship, between P and V, this is the expectation of P. Now, throughout this course, we've made use of the total probability theorem a lot. And we sometimes said this is the divide and conquer principle. It will be continuing to help us in the computation of densities. So by conditioning on certain events and breaking up the sample space into events into a partition of events, we can compute the density of a random variable using conditional densities combined using the total probability theorem. So let's see an example. So suppose we have a partition made of AIs, A1, A2, A3, and so on. And we're trying to compute fx of x. We're trying to compute fx of x. We have available to us fx given a, 1, fx given a2, x given a2, up to fx given a n, x given a n. What do we know? A1, A2, up to AN are a partition, a disjoint partition of the sample space. Okay? So how do you think we can compute fx of x using the joint, the conditional, densities? Let's remember that probabilities of infinitesimally small events can be thought of proportional to the density. Okay, so let me clarify that. Remember, the probability that x is in a small area, x2, x plus delta, is roughly fx of x times delta. This becomes more and more correct, of course, as delta goes to 0. So now think about this probability. Now suppose we're breaking this probability into a summation using the total probability theorem. How would that proceed? We would write this as a summation of probability x is between x and x plus delta given ai times the probability of ai, right? And sum this over all I. But now think of this small delta, and you can approximate this probability, this conditional probability, by the conditional density multiplied by delta, right? So this is roughly equal to fx given ai of x times delta. Now thinking about this, can you tell me how would we combine these densities, conditional densities, to get the unconditional density? Here we have fx of x times delta approximately equal to fx given ai of x given ai, maybe I should keep the conditioning here, times delta. Drop the deltas, and remember we have p of ai here. So fx of x is equal to summation fx given ai times p of ai, which is very intuitive. So that is divide and conquer principle. That we will use. Okay? Let me rewrite it here. Fx of x can be found by fx given ai, x given ai, times the probability of ai. I from 1 to n is arbitrary. The AIs are a partition of the sample space. What are they? They are disjoint sets, and together they make up the whole sample space. And we can extend this idea to expectations, right? Let's extend that idea to expectations. expected value of x. Suppose we don't directly have the Pdf of x, but we have these conditional Pdfs under certain conditions. So how would we be able to find the expectation of x? We have the total expectation theorem, right? This is the expected value of x given ai times the probability of ai summed over all I. So simply compute the inner expectation here by integrating over the conditional density. X times f x given ai dx multiplied by p of ai summed over all I. And the idea, of course, extends to the case where we want to compute the expected value of a function of x. We can write this as the summation over I integral g of x f x given ai dx multiplied by, if you will, let's put the probability of ai factor here, and this is it. Any questions? Is this okay? Let's see the application of this on an example. Very practical example from a real life situation. I think each of us at some point in our lives want to compute the statistics of our waiting time somewhere, because we all wait for something. In this case, we're waiting for a metro train. The metro train arrives at the station near your home every quarter hour starting at 6 a.m. You walk into the station every morning between 7:10 and 7:30. Your arrival time into the station is random and uniformly distributed in this interval. What is the PDF of the time that you have to wait for the first train to arrive? Also find the expectation and the variance of your waiting time. So let's see. Then we need to define a random variable here. I arrive between 7:10 and 7:30. So I can define the random variable x is how much after 7:10 in minutes I arrive, right? What do you think? So my arrival time, if you will, is 7:10 plus x. Units of x are in minutes. Okay? So x takes values in which interval? 0 to 20. Okay. 0 corresponds to arriving right exactly at 7:10, and 20 corresponds to arriving at 7:30. Okay? So I arrive uniformly and randomly in this 20-minute interval. So fx of x is uniformly distributed here from 0 to 20. Height of the density is 1 over 20, of course. I need to compute something about the waiting time until the train. Where do trains arrive? Trains arrive every quarter hour, starting at 6. So there's a train at 7, which corresponds to 10 minutes before I arrive. Okay? Here there's a train. train at minus 10 if you want. It's at 7 a.m. 7 a.m. train. And there's a train at 15 minutes after. Right, there's a train 15 minutes after 7, which corresponds to here, 5. At 5 minutes after 7:10, there is a train. So train at 7:15. 7:15. Okay? Now, there are two situations in this case. If I arrive in this interval between 7:10 to 7:15, then I will take this train. In that case, my waiting time for the train is bounded by 5 minutes. Right? If I arrive later than 7:15, however, if I arrive somewhere here, for example, my waiting time this time can be anywhere between 0 to 15 minutes. Because the next train is at 7:30. So these are the trains. Let me mark the trains by arrows. Train number 1, train number 2, train number 3. Because this corresponds to 7:30. Train at 7:30. So in this example, dividing the whole sample space into two regions seems to be useful. Because if I divide the situation into these two scenarios, the first scenario being I arrive before 7:15, second scenario I arrive after 7:15, it makes it easier to think about the problem. So let's write event A as arrive before 7:15. Equivalently, in terms of the random variable x, this is the event that x is less than or equal to 5, or maybe less than 5. Equal is not important here because we're dealing with continuous random variables. Okay, x is less than 5 corresponds to arriving in this interval. Maybe let me just mark this as A. In that case, this part would be A complement. A complement is x is bigger than or equal to 5. So I have partitioned the sample space into these two disjoint events. Now I can compute the PDF of my waiting time. When A happens, what is my waiting time? My waiting time is basically my arrival time, the difference of my arrival time and the train arrival time, right? So if A happens, then the waiting time, let's call it W, waiting time W, is 5 minus x. Do you agree? If A happens, then the train that I will board is at 5. Okay, at 5 minutes after this 0, okay, which is 7:10 actually. So my waiting time for the train is 5 minus my arrival time. Okay, if I did not arrive before 5, then my waiting time is a difference of my arrival time from 20. Okay? In this case, my waiting time is 20 minus x. Let's compute the conditional Pmf, the conditional Pdf of my waiting time under these two conditions, A and A complement. So we need Fw given A. W given A. My waiting time is 5 minus x. What do you think? Right. My waiting time can be as small as 0 when I arrive right here, and as big as 5 when I arrive here. And it's uniform. Why? Because X is uniform. I'm doing this a little intuitively. After we do this, let's also compute the conditional Pmf of X, and let's do it that way. But first, I want to just compute the conditional distribution, conditional Pdf of W by inspection. This is actually the topic of derived distributions, which we haven't addressed yet. But it's a very simple example, so I think it's worthwhile doing it this way. So this is the conditional Pdf of my waiting time, given that I arrive before 7:15. And this is the conditional Pdf of my waiting time, given that I arrive after 7:15. Let's see. It can be as big, small as 0 and as big as 15. So this is the conditional Pdf. Now all I have to do is join them using the law of total probability. So Fw of W, the density of my waiting time, is Fw given A times probability of A plus Fw given A complement times the probability of A complement. So let's see. What is the probability of A? From here, A constitutes the first 1/4 of the whole region, so it's 1/4. Okay? So it's 1/4 times Fw given A plus 3/4 times Fw given A complement. And when we write that down, we'll have two regions. The waiting time that is before 5 minutes, it can be caused both by an arrival before 7:15 and an arrival after 7:15. Okay? It can correspond to taking the 7:15 train or taking the 7:30 train. And we'll have a higher density when W is less than 5 minutes. What is that density? 1/4 times 1/5 plus 3/4 times 1/15, which evaluates to be, let's see, 1/10, right? And when W is between 5 and, so let's write the lower limit. W, of course, is bigger than 0 and less than 5. When W is between 5 and 15 minutes, the density is simply due to this. Because after 5 minutes, this becomes 0. Okay? So it's simply 3/4 times 1/15, which is 1/20. And 0 otherwise, of course. Let's plot this. Fw of W with respect to W. Between 0 and 5, the density is 1/10. 1/10. Maybe, let me make this bigger. 1/10. And between 5 and 15, the density drops to half, 1 over 20. Let's check if this sums to, if this integrates to 1. The integral of this area is 5 times 1 over 10, which is 1/2. The integral of this area is 10 times 1 over 20, which is 1/2. So it integrates to 1, which is good to know that we probably did not make a mistake. Yes, please.
Do we make assumption that it has to the waiting time? Do we have to make an assumption that it has to get on the first train?
We make the assumption that I get on the first train that I see. Implicitly, we assume that. Now, before maybe we understand this, we worry too much about this, let's also compute the conditional density of X itself. F X given A, X given A. What is this? It's Fx of X divided by the probability of A when X is in A and 0 otherwise. What is Fx of X? Fx of X is 1 over 20. So it's 1 over 20 divided by the probability of A. What is the probability of A? It's this area, which is 1 over 4. So 1 over 20 times 1 over 4, which is 1 over 5, if X is in A and 0 otherwise. Okay? So, let's also compute f x given a complement, x given a complement, which is 1 over 20 divided by the probability of a complement, which is 3 over 4, if x is in a complement. Okay? So that is equal to 1 over 15 if x is in a complement and 0 otherwise. Let's plot the conditional density of X under these two conditions. F X given A is 1 over 5 when X is between 0 and 5. My arrival time, given that my arrival time is between 0 to 5, the density is uniform with 1 over 5 height as expected. And given that it's between 5 and 20, it's between 5 and 20 and uniform in this region. And the height is 1 over 15 as we computed. Okay? Merging these, we can compute fx of fx of x, and you can do that. You can check that as exercise. Before we finish this, let's compute also the expectation and variance of our waiting time. Okay, I'm going to use this space. What is my waiting time? Let's quickly do that. Expected value of my waiting time is equal to the expected value of 5 minus my arrival time, if I arrived in this region, and 20 minus my arrival time if I arrived in this region. Okay? So, let's see. So let's divide this into two cases. It's the expected value of 5 minus x given x is in A, and it's the expected value of 20 minus x if x is in A complement. Okay? So then the expected value of my waiting time using the total expectation theorem is the expected value of 5 minus x given x is in A times the probability of x being in A, which is 1 over 4, plus the expected value of 20 minus x given x is in A complement times 3 over 4. Okay? Now, expected value of 5 minus x is 5 minus expected value of x given A times 1 over 4, of course, plus 20 minus expected value of x given A complement times 3 over 4. Let's compute this over here. The expected value of my waiting time. Now, what is the expected value of x given A? Look here, please. If x is in A, the first region, the expectation of x is 2.5. So we have 5 minus 2.5, which is actually obvious. Okay, if you arrived in the first region from 7:10 to 7:15, your expected waiting time should be 2.5. On average, you'll be arriving at the center of the interval, which is 2.5, and you'll be waiting for 2.5 minutes. Times 1 over 4 plus 20 minus the expected value of A given x given A complement, which is the middle of this interval, 12.5. 12.5 times 3/4. So what do we get? 2.5 times 1 over 4 plus 7.5 times 3/4. And that is our expected waiting time. Finally, let's see if we would get that same result from this PDF of our waiting time. This evaluates to what? Roughly 0.6 time plus, what is this? 7.5 divided by 1.4. Around 8-ish, right? Around, somewhere around here. 625. Show for yourself that you can find this expectation from this PDF as well. Okay? This is the end of our hour, so let's stop at this point. And think about this example. I suggest you redo this example and also think about the variance of your waiting time.